So robustness investigates small changes around method conditions. Talk about robustness, I'm going to talk about big changes for making the method robust, but as far as validation, we want to see, well, what kind of the small changes, if we have one instrument to the other has a small difference in the flow, or the mixing of the mobile phase, or the injector, or the calibration of the wavelengths, do they make a quantitative change in the results? And this is a table that I think we could assemble, and this is unrelated to chiral chromatography. This is something that you would do with a chiral separation too. So this is just sensitivity to small changes. So if we make small changes in the flow rate, do we see differences that might affect the analysis? Make small changes in the mobile phase, what we'd expect, change in retention generally, and certainly in reverse phase chromatography we would. Do we get a change in selectivity? Oh, maybe not, just resolution change, and so on. We just go through this, but the idea is you make small changes, a few percent of the specified conditions, and see, does that affect your separation in a way such that it causes a problem? If you have a yes, and that it affects the separation in a way that causes a problem, then you want to be sure that you set a very tight specification on that, or you have a way to account for it. That is, well, if it has this kind of a problem, you can compensate for it by increasing the mobile phase strength or something like that. And I'm sure you've gone through those kinds of things in your achiral validation. Stability, generally just the solubility of the stability of the analyte solution. We can run, for example, just an overnight run just to show, make repeated injections over the course of time to show that the analyte is stable in the solution, or just a stability study to show that the analyte is stable in the solution. If it's not stable, then the usual workaround is either change the sample solvent or do what we call prep and shoot, just make up the sample and inject it. Okay, so this is probably nothing really new. The only issue is we're dealing with a ratio of a major component to a minor component. But still, I would treat the minor component analysis as an impurity. And so the things that you and your organization do for analyzing impurities would be fairly similar to what you would do with analyzing a chiral component. Improve method robustness. I have these kind of listed in this order. This is not, I think as part of method development, you want to do the method robustness. You don't want that to be a test that you ran later and are surprised by the results. In fact, I think you want to already know what's going to happen from validation. You should have already done some of the experiments around validation to know how good your method's going to work before you hand it off to the group that might validate the method. So the validation and should really just be a formalization of what you already know. Method robustness, I think, is something that should be incorporated in your method development. So we talked about this earlier, where we saw some change in retention of this endocrine disruptor as we changed the mobile phase solvent. And I said, well, we can make little plots, and this gives us a kind of a visual way to see the change. And I hadn't really noticed that before I did this, but I didn't really think quantitatively about what this curve might actually look like. So I think it's worth plotting the data, and it's worth having not just one or two data points, but it's worth having a data set to make sure that you see what the nuanced behavior is. In this case, it's trivial. It's fairly easy to visualize, and maybe not worth a big study, but still have the ideas. But if we go to something that's a little more complicated, then we probably want to do a little more sophisticated study. This is separation of this diastereomer. So I have four peaks. In screening on, I got several separations, but I like this one because the peaks were fairly sharp. So I thought I would try to do the separation on this column with this mobile phase. Unfortunately, in the screen 50-50 methanol ethanol, I got one of the peaks, one of the enantiomers resolved from the other three. So I did some other experiments. I varied mobile phase and I varied temperature, and it looks like kind of the data's like all over the map, so to speak. So I think we need to look at this a little more systematically. And actually these experiments were done in a fairly systematic way. I varied the mobile phase composition from 3:1 to 1:3 methanol ethanol. And for each of these, I varied the temperature, high temperature, low temperature. So with more complicated data, particularly when we have two parameters and it looks like there's some behavior that's a little more complicated, it's often useful to think of this sort of like a factorial design. And what I do is I'll go into a conference room or lunchroom or something and find a table where I can just lay my data out and lay the chromatograms out in the way that they were run, so to speak. And so I can compare, okay, so this is at 1:3 ethanol at high temperature and low temperature. And as I look at it, oh, okay, so I can kind of improve the separation as I go to higher temperature. But at 1:3, I look at this and it looks like, the temperature actually improves, separation improves as we go to lower temperature. Statisticians refer to this as interaction, where you have two component, you have, for example, two parameters, and if you set one of the parameters, the behavior, say like this, we see improving separation at higher temperature, and if we set this parameter at a different level and rerun the experiment, say varying temperature, we see a different behavior. They call that interaction because the actual response, in this case separation, is dependent upon the combination of the independent parameters, mobile phase and temperature. And this can be very confusing. So run it at these two experiments and just vary the temperature and see what that behavior is. Well, I thought maybe I can go to some extremes, either higher temperature or go to straight alcohol. That didn't work out. So I will, but what I did learn is I did learn the separation wasn't going to work and there wasn't any sense continue to beat my head against the wall and so I went to a separation on another column. But this is a factorial design, and sometimes just draw this little box with the different parameters levels, and and we have a center point. I like to do that just because this is often the starting point, and we make the box around that. This is 5 experiments for 2 levels. That's not too bad. And notice the parameters are easily changed, so we can do that in an overnight experiment or just set it up to the day and come back in a little bit and get your results. It doesn't require that you necessarily know what the results are before you do the next experiment. You just have the experiments already run. In fact, this is how you'd fill in a table. We can also just look at the extremes. It's okay. This is our center point, so we'll hold the temperature constant. We'll see what happens when we go to straight ethanol, what happens when we go to straight methanol. Hold it 50-50 methanol ethanol, and what happens when we go to low temperature and high temperature. 40 degrees is the upper column temperature limit for these columns. 10 degrees is a convenient temperature that most LC temperature control compartments can reach. Statisticians refer to this as main effect. Means everything's held constant. We're just looking at the behavior of one parameter change with everything being held constant. So if you want to, you can, it's statistically defensible because statisticians have a name for it. So you could still at least run these experiments. And this is still a systematic approach. You have some idea. You don't know about the interaction, but you do know what the bulk effects is. And I would certainly at least have the center point and perhaps some other data points along this. I often use central composite design because it just is more space filling, gives us more information. But certainly, at least just the main effects is probably an experiment worth running. So this is an experiment that I ran, separation. This was a screening conditions. Had pretty good separation, 1:1 methanol ethanol. Thought, well, let's see what happens as we increase the methanol ethanol ratio. Let's see what the effective temperature is. And so this is a high level of methanol ethanol, high temperature, low temperature, low level of methanol ethanol, high temperature, low temperature, simple factorial design, but you don't even need to plot the data. You can look at it. High temperature is going to give us better separation than lower temperature. And methanol and ethanol seem to have no effect. The ratio seems to not affect the separation very much. So why don't we just go to straight alcohol, and why don't we go to high temperature? That's pretty obvious from these series of experiments. This was 5 experiments to come to that conclusion. We didn't actually need to run all these star points or main effect points. I knew that I wanted to use alcohols at the upper column temperature limit, and so I then just ran those experiments, got a similar retention. Interestingly, the ethanol peaks sharper than the methanol peak, so probably if the later eluting peak is our component of interest, we definitely want to use ethanol versus methanol. But there are some advantages to methanol. One is it's less viscous, so we can probably run it we can run it at a higher flow rate. The other is if this is your main component, this is your analyte minor component, this is your main component, you get better dynamic range because this is probably twice the peak height given the same amount of material. So if you make this at a higher concentration, this peak will be big, but the relative height of this peak will be taller than the relative height using ethanol. So there can be an advantage to having a broader, shorter peak for your main component. And we found this by a systematic approach. It's almost trivial, but I think it was unambiguous. Okay, so these are the things we talked about improving the robustness. Fundamental chromatographic equations help us to predict some of the behavior, make use of library screening. We want to have sharper peaks, evaluate the different alcohols, shorter columns give sharper, taller peaks. So generally want to choose conditions that give us sharp peaks, especially for the minor component, and use of experimental design. Whoops, I'm sorry. And use simple conditions. Less things can go wrong. So in effect, that's what I hope you learned here is that what you know about achiral chromatography applies to chiral chromatography. Much of what I showed you could have been an achiral talk. Talked about validation. It's very similar. Method robustness, importance of troubleshooting, a systematic approach versus a random walk, and the idea of keeping the separations simple. So the last thing is what we can do to help. So we can provide column screening for you generally at no charge. There can be some complications, but in general, there's no charge for that. We'd much rather sell you a column that we know is going to separate your analytes than to sell you, say, a Chiral-Pac IA, which is a really good column, but I have no guarantee that's going to separate your compounds. I'm always glad to talk to people about chiral chromatography. This is my email. This is my email here. My colleagues and I monitor this email box, and we can answer questions if you want to send it to there, or if you want to send it there and also CC me, I'll get it both places. We have a phone number, you can call us, and we have a website, chiraltech.com. Okay, this is my favorite slide because it means I'm through talking, and this has my email address. If you have questions, send me some emails, and I'll be glad to discuss this with you.